Today, welcome to the course. We're almost done, okay, but there's some nice stuff still. Today I want to talk about content distribution and BitTorrent. This is another kind of large system, very interesting large system, because it has some very interesting problems. How do you organize file sharing? Especially since all the participants are selfish and they just want their own file and they don't really want to help. How do you organize that? So it's more than just distributed algorithms. There's also some economic theory, some psychology in there. So that's very interesting. And I'll talk about the BitTorrent algorithm. And this is still used a lot today. There's many developments of that. And if we have time, I'll talk about super peer architectures and peer-to-peer systems. This is another very general thing where all these nodes are working together, but some nodes are more powerful than others, and you want to take advantage of that. And many systems are organized to bring out the strong nodes, which are called super peers. Okay. So again, I'm going to touch on this large system, and we're going to have this very interesting kind of large system. Content distribution. This is a really big thing, and nowadays people talk about Netflix, which is doing content distribution. But there's different kinds of content distribution, and Netflix is the one of the big companies, but there's also content distribution of the small people who have not so much money, and that's called BitTorrent. So Netflix is like the big battalions, but you also have the small people solution, and it's very interesting. So here's the problem. You have a lot of users here, these users. Here it's on the order of 1,000. Okay, so this is from years ago, so you notice this is from 2007, but this problem has not gone away, so it's got even worse since those days, so the solutions are even more important. These thousands of users or millions, they want to see a movie, and here's a server that has the movie. So they want to download content available from a source here, which has limited bandwidth. So the trick is, how do you get everybody a copy from a server that has limited bandwidth? That's the problem, okay? It's clear, right? There's many solutions to this. The solution, the big company solution, they say, who cares, you know, just buy enough bandwidth. Even in those days, 10 years ago, there was plenty of bandwidth in the data centers, and just buy it, rent it, replicate the content, have many, many servers all over the world sending stuff. Okay, fine. Okay, so that's a solution, right? Is it a viable solution? Well, yes, it is for people who have money. CNN, MSNBC. In those days it was Akamai, but now there's many, many content distribution things. It's hard to remember all of them. Cloudflare, StackPath, blah, blah, blah. You just type content distribution, find many. But Akamai was one of the big guys. Akamai is still existing. And Netflix has their content distribution. So if you're a big company with lots of money and millions of users paying you, that's what you do, right? So that's a solution. You rent the servers from everywhere. And it's easier today than it was 10 years ago. But that's not the only solution. If you're a person sitting in your house, you don't have millions like Netflix, you can do a smarter solution. You can use the bandwidth of your customers. You can do a kind of peer-to-peer solution. And let's take a look. So those days, Fedora Linux, which still exists, Linux and so on, they were doing their software distribution already like this. But let me show you kind of an example, okay, of how this works. So here's a simple example. we have users and we have a server. Here's a server. Each user, each machine has an upload bandwidth and a download bandwidth, okay? Download is information going to the person, upload is going away from the person, okay? So you know that. Here, for example, is a server with 1 megabit. You can see it's old, but it's the same. You just add 2 zeros here and it's still valid today. And the download here, look, 256 kilobit per second. It's pretty amazing, huh? Isn't it? Yeah. I mean, I only have, in my fiber installed small house, I only have 400 megabits per second. So I would pay a lot to have this. So yeah, this server could send information to these 4 guys. This one might have less. Maybe it has 64 kilobits. Poor people, guys living in the countryside, sometimes they don't have so much, okay? So this is the kind of situation, right? Okay. Let's attach some numbers to this. You can add 1 or 2 zeros and it's still valid today. Here's a file of 1 gigabyte, 2 CDs. Do you remember putting stuff on CDs? Even a fraction of a DVD, movies or whatever. Okay, you want to transfer this. You have 1 gigabyte, 256 kilobits per second. So that's 1,000 megabytes, 1 gigabyte, 1,000, so it's 2 to the 20th times 8 for the 3 for the bits, 8 bits per byte, 2 to the 23 kilobits divided by 2 to the 8 kilobits per second, 2 to the 15 seconds, 32,000 seconds, 9 hours, okay? In those days, 9 hours for loading this low resolution movie, okay? Can we make this faster? Okay, first question for 1 person. Can we make this faster? Okay, this is a trick question, of course, because what's the answer? Yes. No, okay, we cannot make it faster because there's a limiting bandwidth. We cannot make it faster for 1 person, but can we make it faster for many people? Okay, so let's now see how many clients can the server serve. 1 megabit over 256, so it's 256 kilobits per second. So you can do 4 clients, okay? 1,000 kilobits divided by 250, 4 clients. You can actually send the data to 4 people. And after 9 hours, they each get a copy of this beautiful movie, okay? And 9 hours later, 4 more get it, 18 people. And after 27 hours, even 4 more get it. That's not so nice. Every 9 hours, 4 more people. You can never, it's very hard to give to thousands of people. So that doesn't work very well, huh? So we have to be smarter, okay? Let's try to be smarter on this. And the way to be smarter is to look at the resources. What are the resources that we have? And let's say, so here's our system, server, many clients. The question, where are the unutilized resources? So this is a multiple choice question. The server upload, the server download, the client upload, the client download, or E, there are no unutilized services, we're already using everything. So what's the answer to this? Where are the unutilized services? You tell me now. How would you answer this multiple choice?
D.
Sorry?
D.
D. The download of the clients. Well, no, they're already downloading whatever they can, huh? This is a used resource. What's not used here? Yeah?
C.
C, the upload of the clients. Yeah, they can upload. That's not being used, actually. They're only downloading. That's correct. Anything else? D.
B.
B. The download of server. That is also an unused resource. The server is not downloading, yeah? So it's B and D, the answers. That is correct. You get full marks for that. Of course, this will not be on the exam. So yeah, so B and D. Of course, B is, there's not very much in B, yeah? But, sorry, B and C, sorry. The C, there's a lot here. If I have 1,000 clients, there's a lot going out of the clients that I'm not using it. Okay, so that's the real thing, okay? Okay, so let's investigate this. But before we go farther, let me first make something very precise. A file is a very big thing. A movie is a very big file, but assume that we're transferring small pieces, okay? Maybe 256 kilobyte pieces. So a file of 1 gigabyte will be divided into like 4,000 of these pieces, okay? This will make our examples more easy to understand, to compute. And so not just a big file at once. You divide it into pieces that makes things much easier to manage. So if each client has a download of 256 kilobits, it takes 8 seconds to download one piece, because you have 8 bits in a byte, okay? And if the download, if the poor guy has only 64 kilobits, then it's 4 times longer, 32 seconds. Okay, so this makes this very concrete. So we're looking at these pieces of 256 kilobytes. Okay. So that's one thing. Here is a scenario. There's 2 scenarios, on the left and on the right. We have these blue guys and we have these yellow guys, okay? There are 4 of them on each. The blue guys are getting their pieces, their files, and once they receive the file, the second guy can get it too. So in the left scenario, the yellow ones, each yellow one is attached to a separate blue person, okay? And in the right scenario, all the yellow ones are attached to the same blue person. So the choice of which person they're attached to is different, okay? Let's compute how long all the guys need to get their first piece. So this client is going to wait 8 seconds for the 256 kilobits for getting the first piece, okay? Right? That's simple. And this yellow guy is waiting. First, when the piece is downloaded here, it gets it 8 seconds later, okay? 16 seconds. So we're assuming that the piece is downloaded before it's uploaded to the second guy. That means the yellow guy will get it after 16 seconds, right? And each of the yellow guys will get it after 16 seconds, right? And if you look at the scenario on the right, all the yellow guys here are attached to the same blue guy. So you see that's the only difference, is which blue guy the yellow ones are attached to. So here, in this second scenario, this blue guy will have the piece after 8 seconds. But since now the bandwidth is divided among all these, divided by 4, that means each of these will take 32 seconds. So the yellow guys have to wait 40 seconds, okay? So it's longer here. So you see the choice of which node you connect to will of course affect the time, okay? This is called, okay, so 16 versus 40. This is called peer selection. Okay, it's clear we're going to use the upload bandwidth of all the clients. I'm going to call them peers because they're all doing the same. It's not like client server. They're all playing the same game. They're all the same importance. So a client will connect to another client, and the client has to select which one. And the algorithm we're going to discuss, it makes a difference, right? If you select a good peer or a bad peer, selecting the right peer to connect can make a difference in the speed, okay? That's one thing. So this is an important concept. The clients have to somehow figure out who to connect to. So this is called peer selection. And there's a second aspect, okay? A second aspect which I'm going to show you with another example. Let's say we have 4 yellow ones here. They're each getting a piece, okay? But the yellow guys are also talking to each other, okay? So each yellow one is receiving from here, but it could also receive from 3 other ones, okay? So the download rate, this guy can receive 256 kilobits, okay? But it can upload to the 3 other ones in this example. So it has an upload rate, assuming it's divided equally, of 192, okay? Okay, so that means instead of just receiving from the server, we can cheat in a sense. They can also talk to each other. So again, we have the unutilized resources here. The clients can exchange data between each other. Okay, a client can download from 4 and upload to 3. Okay, so part of the upload bandwidth is going to be used. Okay, but we have to use it smartly. If we do it like in the previous example, it won't work. We have to do something smart now. It's not only the choice of peers. Here's 2 scenarios, okay? The 4 yellow guys, they're receiving a piece of the file from the server or from another guy. In the first example, they were all asking for the first piece. But let's say we do it differently, where they're asking for different pieces. 1, 2, 3, 4. This one is piece number 1, 2, 3, and 4. In the first example, they all receive piece number 1. But that means it's a waste, because they already have the piece number 1. There's no advantage in talking to each other, you see? But in the second case, they all have different pieces. So that means client, this one receives piece 1, this one receives piece 2, and then this one can download piece 2 from client 2 while it's loading a different one, okay? In this case, they can actually have an advantage in talking to each other, you see? So the second scenario is clearly better, because they're asking for different pieces, okay? So it's not only which peer you connect to, it's which piece that you download is also important. Okay, you see that? That's pretty clear, huh? Which piece you download is very important. So this is called piece selection. So there's 2 important things to do on our algorithm. Piece selection. Which piece of the file you download. If the file is divided into 4,000 pieces, you can download them in any order you want. And if you're smart, then you don't do it in the same one as your neighbor, okay? Because if you do different ones, then you can exchange. So piece selection is also very important, you see, yeah? And that means that there are 2 important aspects when we design an algorithm for content distribution. It's peer selection, which one you connect to, and piece selection, which piece of the file you download, okay? Selecting the right peers, selecting the pieces. And the goal is to maximize the total utilization so the download is finished fast. So every peer has all the pieces as fast as possible. Okay. The algorithm we designed, our algorithm has to do these two things. Okay. And there's many ways to do that. Okay. So how do we do it? Well, here's the problem then we have to solve. It's more specialized than the one I showed you a few minutes ago. Given a set of peers with known bandwidths, give a schedule listing all the connections between the peers and specifying which piece should be transferred to which peer first. So you need to know the connections, the peers, and which piece. Okay? This is actually not easy in the general case. In small examples with homogeneous links and small number of peers, you can see what the optimal solution is. Huh? But in a large heterogeneous mess, it's not so easy to solve this problem. So that's the problem we want to solve. Okay? How do you determine that? Actually, it's a hard problem. It's actually an NP-complete problem if you want to find an optimal solution. So that's already, but it's not even the worst part of it. It's NP-complete if you want to solve it optimally, but who will enforce it? Assuming we can make an NP-complete, a solution, assuming we have the solution, who will enforce that schedule? Because the peers are selfish, okay? Each peer, once it has its file, it has no more interest in staying, and it's going away. That means maybe you can't enforce the schedule, okay? Okay? So assume now we have two possibilities. First one is it's some globalized thing. Okay, we have a central authority who organizes everything, says you connect to that guy and you connect to that one and so on. You transfer that piece. You have some orchestration. Okay, that's one possibility, but can it work? What do you think? It's hard, no? Because maybe who's going to force the peers to obey? What if they just don't care? And so that's the second possibility. Assume there's no global knowledge, no machine is going to be orchestrating it, but even if the machine was orchestrating, the peers might not obey. Why should they obey? If they get the file, they're happy, right? Okay, so real peer-to-peer systems is actually this is a very complicated problem. So even the bandwidth is changing over time, peers, they are always connecting, disconnecting, so it's not even a fixed set of peers, and the peers are selfish. This is really a new thing, okay? In our distributed algorithm, this is the first time we see this. We have selfish nodes. Before, in all our algorithms before, you had failure, which was a random thing, okay? Failure is random, is a random thing in the previous algorithms. But now we have a new thing. The nodes are actually thinking about their advantage and disadvantage, and they have an advantage, and they might not decide to execute. Nobody can force them. So the only way to get around that is to do some kind of, is to encourage them, okay? To give them an incentive. So you need some kind of an approach where the selfish way is the best way, okay? You have to give them an incentive to be selfish. They're going to be selfish, but you have to give them an incentive that the selfish way is actually the right way for everybody. You can't just do an algorithm and tell them, now you do this. They won't do it. Okay? So this is the way society works also. You cannot force people to do the best for society, but you give them an incentive. You say, if you work, I will pay you a salary. And the person is working for the salary, and at the same time, the work is benefiting society. Okay? So the selfishness is somehow organized as helping society. That aspect is here also. And this is the first time we have an algorithm now that has to worry about this. Okay? We cannot force the peers. Okay? Okay. So let's first start with a simple solution, and then I'll go to the real solution. Now, the real solution, the one that really got a lot of success, which was BitTorrent. And BitTorrent actually solves this problem. This is the reason why it got so successful. Okay? It solved the problem of selfish nodes. But assuming you just want to do a naive algorithm, you have a central peer, it knows the other peers, and there's randomness. So the basic algorithm is one peer makes random decisions, okay, for peer and piece selection. That's the baseline algorithm, okay? So the baseline algorithm is peer selection. You have randomness, but you make sure that all the peers have roughly the same number of links. So it's kind of homogeneous. And the piece selection is that you're always choosing a random piece. Okay? That would be kind of the baseline algorithm. But this algorithm does not solve the selfishness problem. Okay? Okay. So that algorithm actually would not work. So what algorithm works? Well, the algorithm that works is the first one that really works and became successful is called BitTorrent. And let me introduce some BitTorrent terminology. So we're going to go to the algorithm that works now. First, a little bit of advertising for BitTorrent. This was a huge thing when it happened, and it appeared in 2005. Maybe for you that seems a long time ago. For me that does not seem so long ago, okay? Because the internet was existing for many, many years before this, and no one had a solution, okay? So Wired magazine, which still exists today, the BitTorrent effect. Movie studios hate it, file swappers love it. Bram Cohen's blazing fast peer-to-peer software has turned the internet into a universal TiVo, which is a device that sort of does that. For free video on demand, just click here. So the inventor was Bram Cohen, and his software was the first one that really solved this. And the really interesting thing about this software is how it solves the selfishness aspect, okay? It's a very clever solution. Let's introduce BitTorrent slowly. It introduces a whole set of terminology, and if you really want to understand the deep reason why it works, you have to study economics. Economics, how selfish actors, people, make society work. Okay, so here you have similar idea. You have seeds and leechers, trackers, so these are like basic nodes. You have the notion of a torrent file or meta-info file. You have this concept of choking or unchoking a user. So you can see Bram Cohen has a colorful terminology some places. Choking, you know, étouffer or étrangler. It's like étrangler, choking. That means you don't send any pieces. Unchoking is you can send pieces. Then rarest first. So you have different ways of doing piece selection. And then really a smart notion. This is a technique called tit for tat. And the basic solution of the selfishness uses a psychological approach called tit for tat. Okay, it sounds very weird, but it's a very serious economic notion for how do you get selfish people to collaborate together. The way is tit for tat. And the way is the following. If I'm giving somebody something to somebody and they give something back, well, nobody is going to force them. Maybe they just cheat and give me something bogus, okay? I buy a radio or a computer and it's a piece of junk, okay, that I get back. Well, the way tit for tat works is that you assume that it's not just one buying or selling, but that there's a whole sequence. It's a whole process. And in society, that's what happens. A store is not just selling something to one person, it's continually selling to many people and even to the same people. And the way that to make it work is that you have to make the person happy for the next time. And the way that tit for tat works is that if somebody, if I do something for someone and they give me they cheat, they give me a bad response, then I will punish them for it by not buying from them, for example, or by doing some other kind of a punishment. But only one punishment. They get punished once, and if after that they start behaving normally, I forget the punishment. So tit for tat means that if someone does something bad to you, that you punish them but only once. You don't keep remembering the punishments, okay? And that actually works very well in society, and it works here. And then there's a concept called Pareto Efficiency. Pareto was an economist from the end of the 19th, beginning 20th century, who defined how an economic process works. So we'll talk about that also. Okay. So that's some terminology. Let me introduce some of the basic ideas then. A seed is a node that has a complete copy of the file. They can seed the rest. They have the whole file. The problem is, of course, they have the file, so maybe they don't have any reason to stay on the network, okay? They're usually selfish, okay? But you need at least one seed. You have to at least have a seed serving the complete copy of the file. At least the first seed has to stay. Once the first seed has sent out all the file, then the file is in the system, and maybe nobody else has a full copy immediately, but they all have all the pieces. That means you can find pieces even though there's no more seeds, okay? All pieces of a file must be around somewhere in the network or it doesn't work, okay? So at least the first seed has to stay. But usually that's okay. But you don't actually need more than that. You can have more seeds and it will work better. And sometimes people will stay. Sometimes you actually have nice people who will let their machines keep running the BitTorrent software and they don't turn it off immediately. So that helps, but it's not absolutely necessary, okay? And then you have the other side, are the leechers. The leechers, they're kind of the profiteers. A leech is a sensu, it's a kind of thing that will suck your blood if you walk around in some marshlands. But it's not actually a very nice little animal and it doesn't hurt or anything, but it's sucking your blood. So any PO that does not have a complete file is called a leecher, sucking the blood. But once he has the full seed, then the node becomes a seed, okay? The leecher can eventually become a seed. But maybe there's no seeds, maybe there's only leechers. And then you have a third kind of node called a tracker. The tracker does not have the file at all. It just keeps track of who are the seeds and the leechers, because the tracker is used when new nodes come into the system. So you need a few trackers, but you don't need very many of them, okay? You need a couple of trackers, okay? So with that you have already the three nodes, the seeds, the leechers, and the trackers. So I can start talking now about BitTorrent, okay? How the algorithm works. So we already presented these three concepts, huh? Seeds, leechers, and tracker. You get that, right? Now we can start talking about the actual algorithm and how it works. First of all, how do you start it? If somebody has a file and they want to give it to the public, what does that person do? Well, let's say I have a file, mask of 0, 1 gigabyte, huge file, not HD or 4K. But anyway, you create a meta info file, which basically tells you information about the file, the name, and how it's organized, and the pieces, what the pieces are, how many pieces there are, and it's published. Also, the identity of this guy on put it in a file. This is published on a tracker. Okay. So this tracker has to be accessible. The usual way is to make the file accessible on a web page. So you need a way of getting into the system, and the HTML protocol is used as the way to get in. Okay? So the tracker will put everything on a web page, and if I'm a Leecher, I want mask of 0, okay? I will register myself with the tracker. They will tell me about where to get the torrent files. Okay, and then, so B and C would be Leechers then, who connect into the system. So this is the way to get in, okay? So that's important. The trackers actually only give a list of peers to the people who want to get in. So if a node wants to get in, it needs to know some peers. And the tracker will keep track of some peers. Doesn't have to be all of them, but some active peers. And the node that wants to get in will ask the tracker for a list of peers, and the tracker will return some subset of the peers. Typical number is 40 peers. Okay? So this is like magic number, but 40 works. And the peers, they know some of the trackers. The trackers are like benevolent managers somehow. Sometimes the peers will send statistics to the trackers. So this doesn't matter for the selfishness, because this is just a message. If you run the BitTorrent software, it will do this automatically. Okay? So here I have node H who wants to get in. It sends a message to the tracker, and the tracker will send a subset of peers back to H. Okay? So that's what the tracker does. And once the node actually gets a copy, okay, the node will receive here. Once a peer list is received, then the node will handshake. So the peers, they have to know each other. Okay? So this node will send handshake to all of the 40. They may not be completely in still. Some of them may be gone or whatever. Or maybe here, maybe node E already knows about H from the tracker, or maybe not. Okay? So it sends a handshake. And that's when the algorithm really starts. Okay? Each of these nodes sends a handshake, gets the handshake message, and then the two peers exchange information. And what they exchange is the bit fields. So a bit field, it's a bit vector which has the same number of elements as the number of pieces in the file. And it tells you whether you have that piece. Okay? It's a 1 if you have the piece, and a 0 if you don't have the piece. So it starts off by being, but H maybe has nothing, okay? So this original bit field will have only zeros in there, okay? But as the algorithms evolve, the bit fields will, more and more of the bits will be 1s, okay? So they exchange bit fields. H sends its bit field, and all of the other ones send their bit fields to H, okay? So H knows the bit fields of its 40 neighbors, okay? And that's when H can start thinking about which piece to ask for, the piece selection, and which peer to ask for among the 40, which one, okay? So H has these 40 bit vectors. Okay. So now the algorithm can start. Every Leecher knows what the other peers have, and vice versa. Okay? And so here are two Leechers, A and B. Each one of them has part of the file. They have their own bit vector, they have some of the pieces. And each link, so there's a link here, so each of these has 40 links to 40 peers, but so this link plus others. And the link is labeled by two flags on each side, choked flag and interested flag. And here also, choked and interested, Boolean flags, okay? Choked means I am not willing to send you any pieces. So if A says, I will choke B, that means A will not send any pieces to B. Okay, A is not willing to upload to B. Also interested, A is looking at B's bit vector. Are any of those pieces interesting for A? So A can tell B, I'm interested in some of your pieces, or I'm not. So maybe A is interested, but still B is choked, okay? We'll see. There's rules for this, huh? Maybe A is interested in many pieces in the beginning, but it will only unchoke a small number of the peers, okay? So here on the B side, choked is false. That means B is willing to give pieces to A, and interested is true. B is interested in A's pieces. So B might ask A, please send me a piece, okay? And these flags are going to be updated each time a node sends a request or receives a piece, okay? So the algorithm basically manages the local, the bit vectors, and the flags, okay? And the bit vectors will be regularly exchanged between the two, so A and B can track each other's bit vectors. And that's okay, because even if they're selfish, because A knows that if B is happy, then B will send pieces to A, okay? And A wants pieces, usually, yeah? And B knows the same. So even the selfish node knows that if they want pieces, they have to make the other guy happy, okay? So this works. Okay. So let's talk about peer selection and piece selection. The choking and the interested flags are important for that. Okay? So the interested flag depends on the bit fields. If the other node has pieces that I don't have, then I'm interested. Okay? That's straightforward. Choked is, do I want to send pieces to the other one? Okay? Initially, you choke everybody because it's overhead, but then you will unchoke sometimes, okay? If I'm interested in somebody and that node unchokes me, then I request a piece and then I'm happy. And if I request a piece from that guy, then that guy might request a piece from me, okay? So, you understand that, huh? So now let's understand how the unchoking happens. So unchoking is peer selection, huh? The unchoked peer is the one I've selected for getting information from, okay? And then the piece selection is also a separate thing. So these two are separate things, okay? So let's see how they work now. Okay, let me talk first about piece selection, and then we'll talk about the choking and the peer selection, okay? So piece selection, there are three policies. There's three ways. And you'll see, here, notice there's also an endgame mode. This notion of endgame, actually, we saw it last week for T-Man, that things change near the end of the algorithm. Here you have the same idea, when you have almost all the pieces, but you also have a special thing in the beginning called Rarest First. So you have three of them. Rarest First, Random First, and Endgame. Okay? So what you do by default is each piece is divided into sub-pieces, okay? So you even have smaller pieces, and all the sub-pieces are taken from the same peer. So this actually makes things more efficient. You can actually have different sub-pieces in flight at the same time. And also, it means sometimes you can ask for sub-pieces from different nodes. So dividing a piece into sub-pieces is useful, okay? So now let's talk about the three policies: rarest, random, and endgame. Okay, how do you pick the piece? Okay. Okay. Rarest first. This is a fairly intuitive one. You look at all your bit vectors and you say, I need piece 5, okay? But I have 33 peers who have piece 5, but I also need piece 6. But there's only 2 peers who have piece 6. So you pick piece 6. Choose the piece that is rarest among your peers, okay? Well, some pieces might be very rare in the system, and that makes it very fragile. So you want to reduce that fragility. You pick the piece that is rarest. The one that you want, that is rarest among your peers. Okay? This will reduce the effect of a selfish seed, because the rare pieces will become more common. So this tends to equalize the frequency. Okay? So this is the usual policy is rarest first. Okay? Now, in the beginning, initially, so this is like beginning game, okay? You don't do rarest first, because rarest first is not the fastest. You want to get the first piece as fast as possible. So it's basically a random piece, okay? It could even be called fastest first if you want. That might even be a little better name than random first. But it's a random, from your point of view, it's a random one. You want to get one as fast as possible, even if you get some pieces from different peers. Okay? You want a piece very fast. That makes you useful as fast as possible. So the beginning, initial stage is you want to get pieces quickly, and you don't care which ones. You need some pieces, okay? So the initial stage is random first, or fastest first, if you want, okay? So you see now we have two strategies, huh? The regular one is rarest first, which equalizes. This is during when you're getting the file, but in the beginning, you don't want that. You want something fact quickly, okay? And at the very end, you also do something different. You have only 3 pieces missing. You have the whole mask of 0, but 3 pieces are missing. Ah, terrible. So you only need those 3. You don't need anything else. You're very close to the ends. So in that case, you don't care if the sub-pieces come from different peers. In that case, you break the rule that all the sub-pieces are coming from one peer. You don't care. You need those 3 pieces, okay? So you're going to do a very special kind of selection, focusing on the few pieces that you're missing. And you can even ask for sub-pieces from many peers, okay? So you see, that's how it works, okay? You have three strategies: a beginning, a middle, and an end strategy. And you can see the reasons for them, huh? Okay? Okay, so that's that thing. The other one now is the peer selection. And here's where we have to worry about selfishness. Okay? We're actually going to punish selfish users. So this is obeying tit for tat. Huh? The punishment is only one punishment. You're only going to do a single round of punishment, and then you forget it. And if they start behaving well later, you just treat them normally. But a single selfish behavior, you're going to punish it once. So that's called tit for tat, and that works very well in real life, and it also works well in BitTorrent, okay? So the choking algorithms have two goals, punishing the selfish users, and, of course, using the resources well, of course. So you still want to make sure that you're using all the unused resources, okay? So those are the two goals for the choking algorithms, okay? And what you want, in fact, the way BitTorrent is designed is that it actually tends to something called Pareto efficiency. Pareto efficiency is a concept from economics, and it connects local thing, selfish thing, and global society, okay? It connects actions of people to the global thing of society. If an economic buying and selling, whatever, has reached the point where no two parties can exchange resources and make both of them happier, then we have reached a local optimum, okay? That means everybody has what they want, and there's no way to exchange things, like money, buying things, to make it better for both, okay? That's a local optimization. And that's how people usually work, okay? I want my local optimum, and the person I'm dealing with also wants a local optimum. So if we have something that we can exchange that makes both of us happier, we'll do it. That's a local optimization. And a Pareto efficiency means that when is given certain conditions, that actually leads to a global optimum for whole society, okay? So the local optimization, which is the selfish optimization, also leads to the global optimum. If you really want to know more about that, then you can follow a course in economics, or you can also follow this course, LINFO2345. So I'm making ad for this course. And no, my salary does not depend on how many students are in the course. It's just that I think it's an interesting course. This one is how the internet as a social collection of people doing things, a connected social kind of a network, how that works, okay? So Pareto efficiency is just one piece of that. But if you want to learn more about that, you can follow this course, okay? It's actually starting the next semester, okay? So this is actually an important property, and BitTorrent actually is going to Pareto efficiency, okay? That means using the tit-for-tat approach, the punishment in the choking algorithm, it actually will be converging to a Pareto optimum, okay? Okay, so now let me explain choke and unchoke. Choke and unchoke, there's two goals, There's the punishment of the selfish ones, but also there's, let's make sure the network is being used, okay? Basically, most of it is based on the download rate. Some of the peers are fast, you have fast connection, and some are slow. Some of them download fast, some of them download slow. So you're going to favor the ones that are fast. That's very logical, and that will cause the number of downloads per second to increase, okay? And every 10 seconds, so this is the original BitTorrent, you make a calculation depending on what happened before, who to choke and who to unchoke, okay? You have 40 peers that you have chosen, and the unchoke limit is 4. So you will only be having active downloads from 4 nodes. So that's kind of a magic number, but 4 works well, okay? Okay, so if you really look at it completely, a peer has 80 connections, okay? 40 initiated by that one, but also up to 40 initiated by the others. A peer will only unchoke 4 peers simultaneously, and the decision by the unchoking, okay, is considered every 10 seconds. And the basic decision is based on the speed. But it's a little bit smarter than that, okay? 3 peers are unchoked, if they are interested, of course, in sending things, based on their upload to me, okay? That means if they send me things, then I unchoke them and I send them back. So this is kind of a reward mechanism, huh? If they send me thing and I'm interested, I will send back to them. Show me yourself what you're doing, okay? And the fourth one is random. This is very important actually. In the remaining connections, you look for a fast guy and you pick that guy randomly. And why is that? Because this avoids you getting stuck with a small collection of peers that are only talking to themselves but nobody else. So that's very bad. And the way to do that is to add a little bit of randomness in this system, okay? Fast guy randomly in the 40 remaining conventions. So that gives you 4 in all, okay? And that rotates, of course. That random guy will be changing occasionally. Okay, you can rotate every 30 seconds. So you see there's some magic numbers that you can tune, but they're not so critical. You can actually tune them to make things work a little better. Okay? Okay, and after you finish downloading, you can continue staying in the system. So you assume that the nodes will actually stay for a while, and they will when you run the BitTorrent software. It's not the case that people immediately turn off the thing when it's not. Usually it's run still for a while, and you only upload to very fast, high upload rate users. So as fast as possible, while you're still there, okay, you upload, okay? Okay, so that gives you the basic idea of BitTorrent. So there's these 2 problems, piece and peer selection. Piece selection is mostly rarest first. That's intuitive, huh? The piece that's the rarest, the one that you want that's the rarest among your neighbors, but with a beginning and an end game. And in the peer selection, you start by constructing the first one, so this is the tracker, is getting in, and then the choosing of the unchoking, okay? So this is based usually on the speed, okay? And then of course there's this notion of rewarding the ones, okay? So that's basically how it works. So you can see how the selfishness is handled. It's a very simple incentive, and it's based on the fact that 2 nodes are staying with each other for more than just one piece, okay? For more pieces, that they have a sequence of actions, okay? And the tit for tat works very well for that. And this is actually one of many kind of economics-based algorithms. It's kind of economics-based, huh? And then there's some other technicalities that I'll just mention. Okay, so in a networking course, maybe you heard about NATs, network address translators, and firewalls. Of course, the nodes have to be able to talk to each other. So you need, of course, techniques for getting around the NATs. I don't know if you had that already. You've seen some of that in your networking courses. So I'm not going to say much, except that this is orthogonal to BitTorrent. Huh? It's kind of orthogonal. Has nothing to do with how BitTorrent works, but you need techniques. So there's different techniques. So you have this stun technique, or what's called NAT hole punching. So maybe I will say something, but this is all normally something that you learn in networking. So this is not just for BitTorrent, but also in general, for peer-to-peer algorithms where the nodes have to talk to each other. Okay, great. So that's BitTorrent. maybe I make break now, right? That gives you BitTorrent. Nobody was asking questions. Very simple, very clear, right? Probably many of you have already used it, right? Or something, whatever that's the thing now, Azureus or Idarki or whatever is using BitTorrent inside. Okay, so we make a break. Now I want to talk about super peers. Peers and super peers. This is, since we all know there's so many superhero movies, of course there have to be super peers. No, but many real-world systems are peer-to-peer, where the nodes are actually equals. They're talking to each other and they're doing something, and I'll mention in a minute what it means. And some peers are stronger than others, so they're heterogeneous. And some of them are very strong nodes with huge network bandwidth. Some are very small nodes, like mobile phone usually is a very small node, but a home or a connection here, university, can be a very strong node. And the idea is to organize the system so that the stronger peers are helping provide more services. So they're like the backbone, okay? But to introduce that, I want to talk about peer-to-peer computing. And this is another kind of large system, peer-to-peer. So I'm going to give you kind of an introduction to peer-to-peer computing. This is a big thing, and it was used for file transfer also. This seems to be a big motivation, but also other things. First of all, there's different kinds of peer-to-peer, and if you read articles, you see many different people talking about peer-to-peer, and they don't always mean the same thing. So the first thing I want to do is to try to figure out what does it mean, okay, peer-to-peer, and then we'll talk about different kinds of peer-to-peer. This is an article by a guy named Oram, and he defines peer-to-peer as follows. Is applications that take advantages of resources available at the edges of the internet. So what does it mean, the edge? The edge is what is the opposite from the center, which is the data center. So everything which is logically farthest away. So something like smartphones or machines sitting at home or whatever, okay? And these resources are decentralized. There's no main nodes. They're kind of all equal and kind of sitting around. There's no one center. And they're also unstable. Maybe they get disconnected. You know, the phones, it happens a lot. Okay? It even can operate outside of DNS. Maybe it only has, because the IP addresses are unpredictable for some of these, they are using only IP, and they are autonomous. They are separated from central services. So the applications that use these kind of nodes can be considered peer-to-peer, okay? Embedded systems, or in factories, or wherever, on boats, or even mobile phones. So that's one way of looking at it. So the edges, decentralized, unstable. Okay. Here's another definition of peer-to-peer. Completely different definition. This one is written by a group called the Peer-to-Peer Working Group, which makes standards. People love making standards. This one is clearly made by big companies. Okay. It's the sharing of resources by direct exchange. Two systems, big systems. We're not talking about edge now anymore. Now we're talking about direct exchange between systems without talking to the central server. So like two clients talking to each other. And here's a beautiful phrase. Peer-to-peer computing takes advantage of existing computing power and networking connectivity, allowing economical clients to leverage their collective power to benefit the entire enterprise. Isn't that a beautiful phrase written by someone working in a big company? It means you have already a huge number of people in the company that have machines, and there's already a network. Well, you can do things even without the central server. The employees could actually talk to each other and do direct exchange. And this would benefit the entire enterprise. Okay, so that means you're increasing the efficiency of your enterprise by direct exchange. And so this definition does not talk about edge or unstable or anything. These are all very stable machines sitting in a big company, and they are talking directly to each other. So that's the direct exchange for exchanging resources. That's another definition. So you see, these are actually two opposite definitions. And okay, as researchers in distributed computing, of course, we also have to make a definition. Okay, and not necessarily disagreeing with the previous ones, but it's just a form of distributed computing. Okay, and in this course, we're looking at all kinds of distributed systems. It has a certain set of properties: sharing, resource sharing of resources. Also, the nodes all play the same role. There's not clients and servers. All the nodes are both clients and servers. All the nodes can provide services, but can also ask for services. Okay, so the Leechers and the seeds in BitTorrent is like that. Nodes give pieces, but they also ask for pieces. Okay. The third property is decentralization, so that the system does not have like one central point of control. It's decentralized. That means that there's no one piece that if you remove it, it would break the system. All pieces play the same role. Okay, it's not centralized. So the nodes are autonomous. Okay, this is an important property, which is kind of a stronger version of client-server. And then some consequences: scalability. That means you can have a large number of nodes. In BitTorrent, you can have hundreds of thousands. And finally, it's robust. It doesn't break easily, and it's self-organizing. That's one reason why it's robust. If you bring the nodes together and let them run the code, they will start doing nice things. So it's what you call self-organizing. Okay, you don't need to impose or have like a central node giving orders. The nodes will organize themselves. So this is kind of a general kind of distributed computing. So the edge computing is a form of decentralized system. Okay, the resource sharing, which we saw on the previous slide, is important. Scalability, large number of nodes, is important. Robustness. Notice in the edge computing, the nodes are fragile. On mobile phones, they disconnect very often, which you probably have noticed if you take a train and you're talking with someone. So the system has to resist that. It has to be robust. So these are kind of general properties. And so this is kind of a general way of looking at peer-to-peer. So in our view, this is kind of the nicest way. And each person, like big companies or small organizations, can have a different slice of that. Okay? Let me now talk about the history of peer-to-peer, how it evolved. The first real powerful and popular peer-to-peer system, which does not exist anymore, but in the days when it was there, was called Napster. I don't know if you've heard of Napster. Oh, Napster was a huge thing in the days. It was always in the news, and the reason was that it was getting around copyright. It was doing file sharing. So the way it works is you have a number of nodes here, and they have files. Okay, here, beautiful, nice Britney Spears song or whatever, MP3 files, and you have a central directory. So if I'm here and I want this file, by.mp3, I ask the directory, where is it? It tells me it's here, and then I make a direct connection. This is what we call the first generation of peer-to-peer. Notice it's not completely decentralized, because the directory is central, but the data transfer is not central, is decentralized, okay? So it's only partly decentralized. So what happened was that people were getting around copyright, and this was before DRM, digital rights and so on. People were sending all these files without paying for them. So at some point, there was a legal action against this company, and it's very easy to break this system. All you have to do is turn off the central directory, and it doesn't work, because it's not completely decentralized. But this was already called peer-to-peer, and you can see it's partly decentralized. Okay, so that was the first generation. And then, once they turned off Napster, of course, the grassroots internet community was not going to take it lying down, so they made a version which was 100% completely decentralized. And these systems, their descendants of this still exist today. Yeah? Gnutella and Freenet were like the first ones of this. There's no central directory anymore. Each node has a directory, a partial directory of what it owns, but maybe a few other things. So the node only has a partial information, and it knows some neighbors, but it does not know everybody. Okay? And the way to look for a file on this is to use kind of a flooding. So I say I want Britney Spears song. I have no idea why I would want that, but yeah, no, I could ask for that. Or nowadays, the latest new star is Billie Eilish. Maybe I want Billie Eilish song or something. Okay, I send a message, and it does flooding, and it basically goes to a certain level in the system. And if one of those nodes has the Billie Eilish song, then I will do a direct transfer. So you can see it's not as efficient, because the flooding algorithm is going to be not really as scalable, okay? And there might be hundreds of thousands of nodes in here, but the flooding algorithm would not go through all of them, but maybe would only go through thousands of nodes. And so I'm not guaranteed to find the file if it exists, but notice that every node is basically running exactly the same code. Notice that this system is completely decentralized. It is basically, there's no way to kill this system. If I shut down some nodes, the other nodes will just keep running, okay? So this system cannot be turned off by any kind of a government action, okay? Unless they actually change the underlying internet, and then people will make a revolution or something. But other than that, there's no way to turn this kind of a system off. It's completely decentralized. This is what's called a random overlay network. And at some point, this was in the early 2000s, if you look at all the internet traffic, all of it, the majority of the internet traffic was for these kinds of systems, because they are so inefficient, the flooding, and so many people were using them, that most of the internet traffic was going through these kind of systems, Gnutella and Freenet, systems like that. It's not like that anymore, but that's amazing, isn't it? I mean, even in the early 2000s, the internet was huge in those days. There was already a billion web pages and so on. So these systems were extremely popular, but they had their day, and better systems came later. So this is the second generation, random overlay networks. Better versions of this, more efficient versions that came. And this is called this is the third generation. This is called structured overlay networks, or DHT. DHT is a term you'll see, distributed hash table. And it's an abstraction. It's a hash table. You can do put and get. Okay? All this is implemented by nodes talking to each other. spread over the internet. There could be hundreds of thousands of nodes in here, and they have a particular structure. And so this is the DHT. I will give you an introduction to DHT next week in the last lecture, so I'll explain a little bit how this works inside. But it's a particular structure, and it's very precisely organized, and it's very robust. If one of these nodes fails, then the other nodes will reorganize themselves to make it keep working. That's actually a very interesting thing. New nodes can come in, and the system will grow, and the new nodes will also reorganize, and the whole system actually will scale up. And if the performance and the storage will increase if there are more nodes. So this is actually a really nice abstraction, and actually it was used in some systems. So an early version of Skype was using this, okay? But it looks exactly like a hash table. You have mapping from keys to values. The key can be the name of the file, and the value could be the whole file. That can be a very big thing, huh? And then you have get to get it. And what happens is, the files are stored in certain places inside here, and if you do a put, it will be stored in certain places, and if you do a get, it actually does a kind of routing internally and finds the file. So if the file exists, you're guaranteed to find it, okay? So the neighbors are well defined and not random. So this is a very interesting thing, and this thing started by in the year, actually the very first one was in 2001. It was a system called Chord, and many variants of this were invented later, and it's used very often, still even smaller versions of this, because it's so nice to use. It's easy as an abstraction, and it has an efficient implementation, and it's completely decentralized. So there's no central node here, okay? So you're hopefully now curious, how does this magic thing work, okay? Don't worry, we'll see next time, but not today. Okay, next time I will explain how this thing works. So this is actually the more modern form, and many very efficient versions of this exist even today, okay? That's all I want to say about this now, and next week you'll see much more of this, okay? So that gives you the kind of an overview of the peer-to-peer systems. But now what I want to talk about is super peers. That's also a more modern, smart way of organizing all these peer-to-peer networks, because the peers are not equal. You cannot make a system that's decentralized and the very weak peers give them the same responsibility as the very strong peers. That will make your system worse, actually, yeah? You will have to spend all your time reorganizing if the weak ones are failing, okay? So the peers are heterogeneous. That means they're very different. Bandwidth can be very different. The time they're online can be different. They can either be open IP, maybe they're hiding behind a NAT. They can have high, low latency. They can have high CPU power, low power. Okay, so they're very different. So if you want your peer-to-peer system to be practical, you have to recognize that. So all of the peer-to-peer systems I told you that presented, first, second, third generation, even the third generation, you have to take this into account. And that's where we get this notion of super peer. So all of the modern peer-to-peer systems are actually only really peer-to-peer with respect to super peers, okay? Here we have the super peers, and here we have the regular peers. The regular ones are here, and in the center we have a cluster of the very strong peers, and these are the super peers. So all modern peer-to-peer systems will be organized like this. They will be organized as a core of true peers, which I call super peers, and the regular peers, like your smartphones, will not actually be in the core. They'll be sitting outside, and they'll be more like clients to the real peers, which are the super peers. Okay? So all of the peer-to-peer systems you see today are organized like this. And this is automatically done. This is a self-organizing scheme. If a strong node attaches to the system, it will all automatically migrate to the center. If a weak node attaches to the system, it will stay on the outside. Okay? So that's the idea. So the peer-to-peer systems existing today are all organized like this, and it's all automatic. Okay? So when people talk about peer-to-peer systems today, this is what they really mean, even if they don't say it. Okay? They often will not say it, marketing, whatever. So to understand this, I want to make some quantitative analysis. So I'm going to show you some very interesting graphs of peer behavior. Here on the left graph is the host uptime. It's any node is called the host. It's from 0 to 100%. How often it's up. Okay? And here is what is the percentage of hosts. This is a cumulative distribution function of host uptimes. And this kind of a graph, called a CDF, or cumulative distribution function, is very common. So you have to learn how to read it. So I'm going to go over with you how to read this graph. Okay? It's cumulative. So it will always go from 0 to 100%. Here, there's four, in this example, there's four graphs. Here I'm talking about the Nutella. So this is the second generation one. Napster, the first generation peer-to-peer. And here is Nutella host. So this would be a Nutella node, and this would be the one it's connected to. And this is the internet host for Napster. So this would be, the green one would be any random Napster node, and this brown one is the one that's connected. Okay? So you can see many things from such a graph. So I'm going to explain a few things. So you really have to know how to read this kind of graph. So what it means is that if I look at the 40 here, this is the uptime is 40%. That means 40% of the time, all of the time, the host is up. Okay, it's running and connected to the network. And if you look at this, you go to the Nutella, you see that 80% here. What that means is that 80% of the nodes are up less than or equal to 40% of the time. Okay? So maybe they're up 30, 20, 10%, but not more than 40% of the time. So at 40%, you already have 80% of the nodes here. That means that 80% of the nodes are pretty weak, in fact. Even look at the 20% uptime. These are nodes that are only up 1/5 of the time. It's already 60% of the nodes. That means more than half the nodes are only up 1/5 of the time at the most. That means that these nodes are very weak. They're very often down, you see? If I want a strong network, then it should be close to 100% up percentage. If I want a strong network, then the most of the nodes, it should be like this, It should be like this, where only a small percentage of the nodes are up 80%, and most of them are here, You can see? If you really want strong nodes. So the Nutella nodes are pretty weak, okay? The Napster nodes are actually a little bit stronger here. For a given percentage, they're actually more up, okay? And then the nodes that they are connected to are even stronger than that. That's reasonable, If I have a Nutella node connecting to another node, usually it's going to connect to a node that's stronger than itself, on average. And that's what happens here. So, for example, this violet line here, or mauve line, you can see that this is the host, the Nutella host, the node that the Nutella is connected to. You can see that it's actually much better. 60% of the nodes are up almost 70% of the time, instead of instead of 20%, okay? So these nodes are much stronger than regular GNU Teller nodes, okay? And the Napster nodes are even a little bit stronger than that. So you can see in general the Napster nodes are stronger than GNU Teller nodes, okay? So you can kind of see how to read this kind of a graph, huh? Here's another graph, the session duration. So in the left, I'm only talking about uptime. So I don't know what the length of the sessions are. There can be many small sessions or long sessions with big breaks. I don't really know. It's just a percentage. But here I'm looking at the session duration, the time I'm connected, okay, in minutes. So this is like hours. So 1, 2, 3 hours and so on. Notice Napster and GNU Teller here. They're both pretty much the same. You can see that 60% of the sessions are less than 1 hour, 60 minutes, huh? And there's only a small number of sessions which are actually very, very, very long, okay? Sessions that are at least 300 minutes, so 5 hours, they're only going to be 5 to 10%, starts at 90%. So 90% will be less than 5 hours, whereas that means that 10% or more. So of only very small percentage are living long, okay? But you can see it's still heterogeneous. There are 10% of nodes which have pretty long lifetimes, whereas here you have nodes that have short lifetimes. So half the nodes will be up less than an hour, but you can still have 5% of the nodes which are 10 hours. So they're basically up very long times, okay? So you can see from this graph that how weak or how strong the nodes are. You can see there's a lot of very weak nodes that are not connected so much, but there are also strong nodes that are up a lot, okay? 90% here, that are up between 90 and 100%. Here, the Napster hosts are, there's a lot of them. There's 30% of them are up at least 90% of the time, okay? So you can see they're very heterogeneous. There are weak nodes, but there are also strong nodes. It's not like they're all weak or all strong, huh? So this is very good for super peer ideas, huh? It means somehow we need to pick these ones, pick these as the super peers, and these are the weak nodes. We don't care, but we have to pick these as super peers. You see how it works? So you have to be able to read this kind of graph. Huh? This kind of graph is really occurring a lot. Huh? And here's some more information on peers. Here's the latency. So this was in 2002. Okay. So latency has decreased since then, but not by that much. You can see here that the median latency, so here you can see it's much more vertical, this S curve. That means really the break point is really around 100 milliseconds, or well, in the year 2002. That means 50% of the nodes here had latency less than 100 and 50 had more. But the interval is very small. So in between 20 and 80 percentiles, okay, these are the percentiles, it's only going between here and here. It's only doing this. So it's only going from like 80 to whatever, 200. So in between the interval 80 to 200 milliseconds, we're already going from most of the nodes here, okay? So you can see with this kind of a curve, you can immediately figure out what are the percentiles. You can see, what about very fast nodes? Here's this node, a small percentage of the nodes is very fast. Here, for example, I have 30 milliseconds. It's unfortunately just a very small percentage, maybe 5% of the nodes, okay, are 30 millisecond or faster. Some of them are very slow. Look how slow this one is, 1,000 millisecond, 1 second. So you can see that like almost 10% of the nodes are very slow in 2002. So the internet was really bad in those days. But it will not get much better. But of course latency is limited by speed of light. So a node between Belgium and Japan is it's always going to stay slow. Nothing to do about it. So today this has shifted a little bit to the left. If you are, for example, living in the region of Paris and you are connecting to a server in Paris, you can get 3 or 4 milliseconds latency. You can be here these days, okay? I know that because that's how it's in my house, okay? And here on the right is another graph. No, one thing here also to say is that, again, it's heterogeneous. It's not perfectly vertical. If it would be perfectly vertical, then all the nodes would be the same, okay? They are fast nodes, which are here, and there are slow nodes, which are here, okay? And there's a lot of fast nodes. So the super peers would be like here, and these nodes would be like very weak smartphones or whatever. But this would be strong nodes, like the server in our department is a very strong node. The university has a very good internal network with multi-gigabit connection to the rest of the world and so on. So we're sitting here. So when I'm in my office, I'm very happy since I'm here. Whereas when I'm with my phone, I'm not happy since I'm here. Okay. So that's this graph on the left. The graph on the right is another kind of graph, really interesting one. Here we have throughput, bandwidth, and latency. Bandwidth and latency are the two main properties of a network. So kilobits per second here, and here we have millisecond latency. Okay? And each connection is a dot. So the dense parts are the more common combination. So if I have 1,000 kilobits per second, this is very dense. So there's a lot of nodes here, but they're all close to 100 milliseconds, okay? Here I have a little island, which is faster, 30 millisecond maybe, or 50 millisecond. And, but it's, the latency is a little bit worse, but it's very fast, okay? What I really want is low latency and high bandwidth. I want to be here, but there's not so many dots here. Notice there's these two horizontal lines. That's very interesting. That's because of the structure of this network that they're measuring. That means there's a lot of nodes that are at 100 milliseconds from each other, but there's also a lot of nodes that are a little bit more. Maybe there's like one extra hop or something, depending on the routing structure. Here it's like, would be like 200, 1 and 200 milliseconds, maybe 1 and 2 hops or something. But notice really the biggest density is here. So this gives you the combination. And if you want a certain magic property, you can look in this two-dimensional space, okay? This graph also, you can see it kind of very frequently when people make network measurements, okay? That's also a very nice graph. So these kinds of graphs, you have to read them, they have to be very easy to read, like reading a book. You look at it, you see right away what's going on. Here's another one. We're not done with the graphs, okay? So again, these are CDFs, okay? This is bandwidth now. How many IPs, so how many IP addresses have a particular bandwidth. So now we're looking at bandwidth, okay? So it's similar to some of the previous one, but this is with particular kind of file sharing called fast track and direct connect, okay? So again, you can see there's kind of an S shape here, S shape, and it's not perfectly vertical, so they're heterogeneous. So we have some very good nodes here with high bandwidth, okay? So like the percentile, if we look at the top 10% of nodes for this one, which is source, it's measured from the source here, to the destination. This one, then we got at least 1,000 kilobits per second. The top 10% have at least 1,000 kilobits per second. The lowest 10% have oh, these must be dial-in modems or something that have like 20 kilobits per second. I hope none of you are in this situation, huh? Not today. So you can see they're very heterogeneous. There's very bad ones, but also a significant number of good ones here. Huh? And the same here, okay, for these two pieces of software. So this was in 2004, huh? This kind of graph tells you that it's heterogeneous, okay? And now we can go to super peers. Now we see that it can work. The super peers can work. All the graphs I showed you before show you that the peers are heterogeneous, okay? They are heterogeneous, which means there are good ones and there are bad ones. So the super peers will be the good ones. So super peer is a node that is both a server to a set of clients and an equal in a net of super peers. So this is basically saying this, okay? They have high utility relative to non-super peers, okay? Somehow better. So you have to measure the utility, yeah? Bandwidth, uptime, or CPU power, okay? Okay, they have good goals, fine. So here is the architecture. So it's basically what I just showed you. The super peers are actually connected amongst themselves, and the ordinary peers are clients to this, okay? We're going to talk a little bit about design issues, but this is very usual. I'm not going to say so much. For example, peer to super peer connections. So when a peer here connects to a super peer, usually it will connect to more than one. And the reason is, if there's a problem with this super peer, then we'll fail over to that one, okay? So a super peer is very good, but it's not infinitely good. So you need some kind of redundancy and fail over, okay? Also, what is the topology inside here? What is inside here? Is it a DHT or is it something else? Typical one would be something called a gradient topology, okay? How do you do promotion? How do you decide when a peer becomes super peer? Okay. Okay, so there's a lot of services. I'm not going to say so much. Skype in those days used super peer architecture. I'm not sure what they do today. Probably it's more data center based. But the data centers themselves are going to be like the super peers because Skype is now owned by Microsoft, and there's it has dozens of data centers over the world. So probably, of all different sizes, so probably the data centers themselves will be kind of super peer, but who knows, since it's proprietary, okay? Okay, this doesn't really say, topology. Right, let me talk about different topologies. It could be random network, like Nutella, where they're just connected randomly. It could be DHT, that's actually not so much used, or was in those days, or it could be gradient. This one is nice. Let me talk about gradient topology, okay? Gradient topology is really nice because it's completely automatic, self-organizing. We don't make any distinction between peer and super peers. It means a node comes in, and automatically, if it's a strong node, it will go to the center. Okay? Okay? And it's actually using gossip, what we saw before, to do this. Okay? The peers will gossip with their neighbors. It's a little bit like the topology management. The strong ones will migrate to the center. Okay? So each peer has two sets of neighbors. A set of neighbors that are similar to themselves. So if they're strong, it'll be only strong neighbors. And a set of random neighbors. That means the whole thing is connected, but the strong peers will only be connected to themselves, okay? The peers gossip to maintain these sets of neighbors. And you can imagine how it's done, huh? It's a version of T-Man, okay? You will gossip and maintain sets of similar neighbors, and also maintain random neighbors, okay? So this is done using gossip. Note the connection with gossip and gradient. And automatically, the highest utility will be in the center. This structure will automatically appear, okay, like magic, because of the gossip. And it turns out, search is actually very practical. Notice search in Nutella was very hard because of the randomness. Here, so if we have random, if I want to search something like a file, I'm in a random network, I have no idea, it could be anywhere, right? But in the super-peer network, it's very easy to go uphill. It's a gradient, so it's like a mountain, okay? The super-peers are on the peak, and these are all in the bottom part, in valleys. So in order to do a search, you just have to climb up the mountain. You go to the stronger neighbors until you reach this center core, and the center core will have some kind of an algorithm to do the search. But each of these nodes will be very strong, and there will be a very small number of them, okay? So the search is very easy. You just go climb the mountain here, okay? So it turns out that search in a super-peer architecture with gradient topology works really well. So many systems are actually doing like that, okay? Let me now say a few things about promotion. This thing is completely self-organized. There is no central authority telling you when you are becoming a super-peer. It's automatic, and it basically is part of the gossip. If you are stronger than your neighbors, then you will automatically group together with stronger neighbors, okay? And sometimes you can officially label a peer as a super peer because the regular peers will only be clients, whereas the super peers will be true peers, okay? So at some point, at some level of utility, you will be officially declared to be super peer, okay? For example, maybe you have some requirement, you have a certain strength, or maybe the top 5%. The top 5%, and this requires global knowledge, but we know how to do that with gossip, okay? We can find that information. So this promotion is completely decentralized, okay? It's a distributed promotion. There's no centralized, okay? Okay, and so you will automatically, the system will always be converging towards this gradient super-peer algorithm, okay? Okay, here I'm not saying so much. You select the peers with the highest utility. It could be session time. So the peers will always measure their utility, yeah? How often are they up? What is their bandwidth? What is their latency? Are they hidden behind a net or not? The peers, they know that, huh? And the neighbors, they know it too. And this is what the promotion algorithm is going to use, huh? Okay. Okay. Now, I want to show you some more graphs. And this is actually related to the small world network that we saw before. Okay. And this is actually power law relationships. Power law relationships. And again, so this is something you find very often. This is related to small world networks. It turns out the gradient topology is going to be a small world network, of course, and it will obey certain kind of structure, which is called power law. But maybe I don't have enough time to say it. I'll just say one thing to fix your intuition, and then we keep the rest for next week. Many real-life things are organized in terms of power laws. So here's an example. This is cities on the Earth, and this is the percentage of the cities, and this is the population. So if there's a city with 200,000 inhabitants, we count how many there are, and this is the percentage. So there are lots of small cities. So here we have the small cities, they're high in percentage, and there's a small number of cities, small percentage with high population, okay? So cities like Tokyo or Paris or something, there's not so many of them, but cities like Louvain, there's many of those small cities, many more. This graph on the left is not so useful, okay? It's much better if you display it log-log, logarithmic, both on the two axes. So the population is logarithmic, and also the percentage is logarithmic. If you do that, you get a straight line. So if you increase the population by 10 times, then the percentage will reduce by some fraction. It depends on the power. Maybe it's a square. So for example, if you increase by 10, then the number of cities will be reduced by 100. But the actual fraction determines the slope here, depends on the system, okay? And for internet systems, you have different power laws. But the point is, it's a straight line. It's a really interesting law. The number, and it's true for cities, the number of cities with a certain population will decrease according to this law. That's amazing, isn't it? Because nobody directed that. Cities are growing automatically. They are growing because people want to live somewhere. People move. There's no earth-wide rule. It says it's like this. But it turns out it's like a straight line. It's very close to a straight line. Okay? And this is related to small world networks. And many internet things are like that too, which we will see next week. Okay? So next week we'll start by power laws, and then I'll talk about DHTs, and hopefully I can finish by showing you the raft algorithm. And that'll be a nice end to the course. Okay, so that's all for today. Okay. That's exactly.